Hello, so in this video I need to point something out to you which you need to be so careful of, right? Let's suppose I've got a function, y is equal to t squared, okay? And then I go ahead and I differentiate it. So I'd write dy by dx is equal to... Hang on a minute, let's look at my function again. I've got y on the left-hand side, that's fine, that's what I'm used to. But instead of having an x on my right-hand side, I've got a t on my right-hand side. Does that matter? Well, yes, it does in terms of my notation, because let's just think about this. I've got a y on my left-hand side, then it's in terms of something which has t in. So it's a function on the right-hand side involving t. So when I draw that on a graph, I'd still have my vertical axis as my y-axis, but my horizontal axis now wouldn't be an x-axis anymore, it would be a t-axis. So when I go through the whole first principles jobby and find the gradient, my change in my vertical distance would be dy, but the change in my horizontal distance wouldn't be dx anymore, it would be dt. So my gradient is given by the change in my vertical distance divided by my change in my horizontal distance. So it would be dy by dt now. When I differentiate, it would be dy by dt. Okay, so I can't actually find dy by dx of this function because that's just going to be 0. There is no dx's in there. There's no x's involved. Okay, so instead, if I wanted to differentiate, I'd have to write down dy by dt. And then it's still the same process. So the power climbs down, so it's going to be 2t, and then it reduces by 1, so it's just going to be 2t to the power of 1. Okay. Well, let's suppose I had something like this then. So again, I couldn't find, it wouldn't be dy by dt, would it? It wouldn't be dy by dt, or would it? Because look, on the left-hand side, I've got a function in terms of z. So I've got z is equal to my function in terms of t. So when I draw this on a graph, I'm going to have z as my vertical axis, and I'm going to have t as my horizontal axis. So then I go through the whole first principles jobby, I find that the change in my y direction, or my change in my vertical direction, is now my change in my z direction, dz, okay? And the change in my horizontal distance direction is dt. So when I find the gradient, it's the change in my vertical distance as dz, divided by the change in my horizontal direction, which is dt. So when I differentiate, it would now be dz by dt. Okay, and it's still exactly the same process. The power comes down and reduces by 1. Okay, so what can we say in general then? Well, if I write down dA by dB, okay, I'm being very general here, but the dA corresponds to my function. My function, which is like my y-axis. Okay, this is my function bit. And then the bottom bit on the denominator is the stuff that my function is in terms of. Okay, so the function that my function in terms of. So that's my horizontal distance. So here it would be a is some function in terms of b. Okay, and I'd draw that on a graph by saying, well, I have a on this axis and b on this axis. Find my vertical change, which is dA. Find my horizontal change, which is dB. Okay, which then means that my gradient is going to be dA divided by dB. Okay, so in general, if I have a as a function in terms of b, okay, then the function bit, the derivative of my function goes on the numerator, and my stuff that my function is in terms of, so in this case b, goes on the denominator. So suppose I have L is equal to 7w cubed plus 4w squared. How could I differentiate that? How would I write down the derivative of that? So will it be dl, as that's my vertical change, right? That's my l-axis, l-axis, and then it's in terms of w, so that's going to be my horizontal axis, right? So it'd be dl by dw, okay? And then I just do exactly the same process, bring the power down, so it's going to be 21w squared plus, well, that's going to be 2 times 4, which is 8w, okay? So same process. Now, you may say, is it really important? Like, you know, if I wrote that in the exam, surely they'd know what you mean. Well, yes, it is important, actually, because we don't just have to have functions in terms of one variable. You won't look at them at A level, but you don't just have to have functions in terms of one A level, in terms of one variable. So, for example, you might have y is equal to x squared z, for example. Well, then you can differentiate with respect to either the x variable or the z variable, right? So you'd write dy by dx, okay, and that would become then 2x, and then the z would come along for the ride. Okay, but you could also write down dy by dz, okay, in which case the x squared would come along for the ride, and you differentiate the z, which just become 1. Okay, so it's really important to get this notation right now.